questions for me? Your midterm is next Tuesday, right?
Yeah.
You have any question? Yes.
So I worked it out about last class equations of motion. Three different methods, right? And every method has different.
They should be all equivalent for sure. You can derive each one from the other. So like problem 4 in last homework 2 is supposed to be a bit hard problem. You can do it by you have to write down 2 equations of motion for the rigid body and the plane, but in addition you will write down 1 angular momentum equation. The solution is posted, by the way, if you didn't see it. So you have to write down 1 angular momentum equation. This can be about the hinge point A, the body. It can be about the center of mass, right? Or you can derive this from Lagrange's equation. So 3 different methods. Each one will give you a different equation. So they are not exactly the same, but if you manipulate one, you can get the other. So I'm saying, so if you divide by some constants and substitute from one equation into the other, you will get the next one and the next one. They are all equivalent. They result in the exact same dynamics. They might not look exactly the same. Any question? So let's continue today with our Lagrange's equations. So we're going to keep just writing this equation over and over again. It's this magic equation. Partial L, partial Q, J dot minus partial L, partial Q, J equals the non-conservative force which we trained over last time. And you did an awesome quiz. Almost everybody got final mark. Then we said, what if we wanted to account for constraints? So we need to add something like Q constraint J, right? And we want to know what is that. This equation is valid for all J1 up to your number of generalized orbits. Okay? Where you know L is simply T minus V, your kinetic minus potential. L is your Lagrangian. Then for this constraint, we have 2 types of constraints. Holonomic constraints, which we discussed last time. Right? If you have your constraint is represented by an expression. It's function of Q1 up to Qn. This is equal to 0. This is the kth constraint. Okay? Which represents some surface in your Q space, the configuration space. And your constraint force is simply perpendicular to this guy. This is F constraint. This is what we discussed last time, which means it's simply a scalar multiple of the gradient of this relation that describes the surface. A force coming from a scalar function, we call it a monogenic force. So the force that maintains a holonomic constraint is a monogenic force. I mean, that's okay, it's not a big deal. At any rate, this is lambda times partial epsilon, partial Q1 in the Q1 direction, partial epsilon, partial Q2 in the Q2 direction, so on. So in particular, the component of the constraint force in the QJ direction is easily written as lambda partial epsilon partial QJ, right? So we're done with holonomic constraints. If you have a holonomic constraint, give me the expression. I have x squared plus y squared equals L squared, for example. When I'm gonna write the x equation, I'm gonna differentiate this partial with respect to x, and that's it. Put this term here, lambda times partial epsilon partial x. When I'm writing the y equation, I'm gonna put the same lambda partial epsilon partial y. Lambda is unknown. So we're done with holonomic constraints. We didn't have examples. We're gonna have examples today, but we discussed them in detail last time. Non-holonomic constraints, on the other hand, we mentioned them. We did not discuss in detail. We said that the constraint is inherently on velocity, it's not on position. So your psi k is something like from j1 to n, some coefficients that can be actually functions of positions, but they are linear in velocities. One example that we gave last time is when you have a car, right? So this is the velocity vector of your car is aligned with its axis. So right here I have my car is moving this direction by x dot, y dot, because x and y are coordinates of the center of mass, and theta is this angle. So the constraint is that the car cannot have a velocity component perpendicular to its axis. So the velocity component along the blue line is 0. This is your constraint. So simply get the components of x dot and y dot along the blue line and equate it to 0. So this is what? X dot sine minus y dot cosine is equal to 0. This is your constraint, and you can see that it's right on this form. Something multiplying q1 dot, something multiplying q2 dot, and 0 multiplying your q3 dot. Your q3 here is theta, right? I have 3 degrees of freedom for the rigid body in the plane x, y, and theta. So I have 3 degrees of freedom subject to one constraint, and I cannot use this constraint to remove one of the degrees of freedom. You cannot reduce the problem. Okay? Any question about that? Another example for the non-holonomic constraint is the rolling without slipping. So if this is x and this is y, and say I have a disk rolling with the surface without slipping. So, okay, how many degrees of freedom do I have? Let's see. I have x and y for the center of mass of the disk, okay? And the disk is rolling. So you have theta, the roll angle for the disk, okay? And the disk may have hitting angle, maybe hitting this way, maybe hitting that way, because we're in the plane. So actually, if this is the trajectory of the guy, this may be the trajectory of the guy, okay? So if you do here, this is the instantaneous velocity of the rolling, right? Because the rolling, you have here r radius. So r times theta dot gives you this black line, okay? The instantaneous velocity due to rolling. In general, it makes an angle. This is another degree of freedom. So we have x, y, theta, and phi subject to rolling without slipping. So here's our constraint. Rolling without slipping. Let's see how to write that. What is the general condition of rolling without slipping? What's the physical meaning of that? What's the physical meaning of rolling without slipping?
Friction, there is friction.
The velocity of the point that you move from
Yes.
zero.
Is that simply there is no slipping? It's called without slipping, no slipping. So this green point does not slip with respect to the floor. Okay? They have the same velocity, the floor is fixed, so this green point should have total zero velocity in all directions. So let's get the x component of it equated to zero, the y component of it and equated to zero. I have two contributions. I have x dot y dot from the center of mass, and I have the contribution of the black thing, the rolling. So I have the velocity of the whole rigid body moving forward or sideways or whatever, but the rolling induces some velocity of the bottom point, which is the black one. Okay? So what's the total x component? Well, I have x dot coming from this point, and the r theta dot gives me some x component, right? R theta dot cosine gives you the y, and sine gives you the x. So this is negative r theta dot sine phi. This should be 0, this one constraint. And the same for the y. You have y dot coming from the center of mass, and the rolling gives you this contribution minus r theta dot cosine phi. Again, this is 0. So two constraints. And you can see that the constraints are inherently on velocity. They are linear, right? Linear in velocity. Something times x dot, something times y dot. The same here. Something times x dot. The coefficient of 1 is 1. Because we need these coefficients to have the constraint on the standard form. The coefficient of y dot here is 0. The coefficient of theta dot is r sine phi, negative r sine phi. And here there is no coefficient for x dot. There is coefficient for y dot, which is 1, and coefficient for theta dot. So here I have two constraints, psi 1 and psi 2. Okay? Each constraint comes with its own psi. Any question about non-holonomic constraints? They are inherently on velocity, not on position. The issue is that you cannot use this equation to produce a relation between positions. Because if I have a relation between positions, I can use this equation to remove one of the positions completely. Okay? Here I cannot do that. You cannot get theta in terms of x and y. I can get it in terms of x dot and y dot, but this is not useful. Okay? Any question about the holonomic or non-holonomic constraints? The meaning of them? Any question, please? If you have a question, do not feel shy. This is the rule here. Okay, so how are we going to deal with this guy? So I don't care about these things. I just care about solving the problem. So how will I solve the problem? Here is your Lagrange's equation. So I'm only interested in how can I modify my Lagrange's equation. If I have a holonomic constraint, here is how I will modify it. I will add one more unknown representing the constraint force, or lambda, with each constraint. So if I have multiple constraints, I'm going to simply sum over the number of constraints. K equals 1 to little m. This is k, this is k. Okay? So I know how to modify my Lagrange's equation if I do have holonomic constraint or multiple of them. Okay, what about non-holonomic constraint? It turns out to be exactly the same. Because you have a holonomic constraint like this. What is psi dot? Psi is a function of q's. What's psi dot? Function of q1, q2, q3. What's psi dot?
Function of q1 dot, q2 dot.
Yeah, how can I write it? You have a function of q's.
Partial q1 by partial q1
Partial
dot.
psi, partial q1 times q1 dot. And I add a partial psi, partial qn dot in general, so it's summation over all the q's, partial psi, partial qj times qj dot. So what do you think about this? This actually has the exact same form as a non-holonomic constraint, right? And okay, what is the useful part? What is the relevant part that you needed to modify the Lagrange equation? What is the relevant part? Well, I just needed for each little q, I need partial psi, partial this little q. That's it. This is all what I need, right? Yeah, which is this guy, right? It turns out that this guy is the coefficient of the velocity in this form. So if I am given the constraint initially on this form, linear in velocities, I simply need these coefficients. Okay? So now, to summarize, I'm given a holonomic constraint or a non-holonomic constraint. If I'm given a holonomic constraint, this is okay. If I'm given a holonomic constraint, actually I'm going to differentiate it to write it in this form. Now, in either case, the constraint is written on velocities. And I'm going to take the coefficient of the velocity. This is the part that I needed to put there, okay? In Lagrange's equation. So in summary, here is your Lagrange's equation. d by dt, partial L partial Q J dot, minus partial L partial Q J, equals the non-conservative J we did last time, plus a lambda times the coefficient. This is like partial psi, partial q. Okay? And if I have multiple of them, then I'm going to have summation over the constraints. And this equation is valid for all j's. This is the most general form of Lagrange's equation. We will not generalize it further. We'll just keep applying that one. I think we trained enough on the left-hand side. The last time we trained enough on the first term of the right-hand side. So today we're going to have a couple of problems on how to formulate this one, although it seems easy. Let's do it.
So now this equation, it is not dependent upon whether we have this type of constraints or this type of constraints.
Exactly. If I'm given a non-holonomic constraints, I have the coefficients of the velocities already. If I'm given a holonomic constraint, just differentiated, now it becomes linear in velocities and take the coefficients. Okay? So let's have this example. X and Y, mass 1, mass 2. And they are constrained by a rigid constraint of length L. How many degrees of freedom do we have? How many degrees of freedom? In total? 1. Anybody doesn't see that it's 1? Okay? So it's 1 degree of freedom. If I can solve